Welcome to the dreaming brain, where time slows and darkness gently wraps around the mind. Tonight, we travel into a hidden corner of the universe, a realm where matter is crushed into unimaginable forms, where silent strength bends the very fabric of space. These are the remnants of brilliance long extinguished, waiting in stillness for us to lean closer and listen. Imagine a clock on the wall. Its hands have frozen in place, stuck at some arbitrary moment that refuses to pass. Yet, if you sit quietly in the room, you will notice the sunlight drifting across the floorboards, the shadows leaning in different directions, the hum of the world carrying on. The clock is silent, but the world seems to move. That simple image is a doorway into one of the strangest ideas ever conceived in physics. The possibility that time itself, at the most fundamental level of the universe, does not exist at all. We live our lives chained to clocks, morning alarms, schedules, deadlines, birthdays, lifespans. Every heartbeat feels like a tick of a cosmic second hand. Time appears obvious, undeniable, a river flowing forward that carries us whether we wish it or not. And yet, behind the surface of experience, scientists have discovered that this river may not be real in the way we imagine. Our familiar sense of passing moments could be a carefully constructed illusion, a story told by the brain to impose order on change. The thought is unsettling. We are accustomed to measuring our existence by the passage of hours and years, by the aging of our faces, by the sequence of memories piling up behind us. If time were revealed to be a mirage, would it make our lives meaningless? Or would it open a deeper truth that what matters has always been the pattern of relationships, the dance of energy and matter, the connections that do not need a ticking clock to exist? Physicists in the 20th century began to unravel the familiar view of time. Einstein showed us that the seconds of one observer are not the same as the seconds of another. A clock carried aboard a speeding spaceship or balanced on the edge of a black hole will disagree with the clock in your hand. Time dilates, stretches, bends under the weight of motion and gravity. What was once seen as absolute became relative, woven into the very fabric of space. Yet even Einstein did not abolish time. He simply transformed it into a dimension. You could map events in 4 coordinates, 3 of space, 1 of time, and the equations would work. The river was stranger, but it still flowed. But as physics moved into the quantum world, where particles flicker and interfere like ghostly probabilities, the river of time became harder to locate. Quantum mechanics lives on probabilities that evolve with respect to a parameter we call EIT, the familiar time variable. General relativity, on the other hand, describes the geometry of the universe itself, and in that picture, the notion of an external clock does not exist. When you try to combine the two theories into a single description of the entire universe, something remarkable happens. The time variable disappears. This vanishing act is embodied in what is known as the Wheeler-DeWitt equation. It is supposed to be the fundamental equation describing the wave function of the universe, the quantum state of everything, all at once. Yet, unlike the Schrödinger equation of ordinary quantum mechanics, the Wheeler-DeWitt equation has no explicit reference to time. There is no derivative with respect to t, no rhythm of change written into its heart. It suggests that, at the most complete level of description, the universe simply is. It does not evolve, it does not unfold, it just exists, in a timeless stillness. The metaphor of the stopped clock becomes haunting here. Perhaps the entire cosmos is like that clock. Its face is frozen, its hands unmoving, yet within it there are patterns that our consciousness interprets as flow. The play of entropy, the increase of disorder, the alignment of memory with what we call the past. All these conspire to produce the sensation of passage. But behind the sensation, the universal wave function does not tick forward. This idea has profound consequences. It means that what we call the present might not be uniquely real. The past is not gone, the future is not waiting. All of it exists together in one vast static architecture, like a block of crystal with every layer present at once. Our awareness moves as though along a slice of that block, giving us the feeling of motion, but the block itself does not move. Philosophers have called this the block universe, a reality in which time is not something that passes, but something that simply is. And yet, as unsettling as this vision is, there is also a strange comfort to it. If the universe is timeless, then nothing is ever truly lost. The laughter of a child, the formation of a galaxy, the fleeting glance between lovers, each of these moments is preserved, not in memory alone, but in the very structure of reality. They are not swept away by the current, for the current does not exist. They are facets of the block, shimmering eternally, waiting to be touched by the wandering perspective we call consciousness. The story of how we reach such a bizarre conclusion spans centuries of thought, from Newton's belief in absolute time to Einstein's flexible space-time to the clash between quantum mechanics and relativity. Each step has peeled away our naive certainty about the nature of reality. What began as a simple human intuition, that time is a universal river flowing from past to future, has been eroded until we are left with something altogether stranger, a cosmos where time may be no more fundamental than temperature or color, an emergent quality that depends on perspective. To appreciate this fully, we must retrace the history of time in science. We must look at how Newton shaped it into a universal backdrop, how Einstein twisted it into relativity, and how the quantum world pushed it toward disappearance. Each chapter will bring us closer to the Wheeler-DeWitt equation, and to the sobering possibility that our experience of time is nothing but a delicate mirage layered over timeless being. And so, we return to the image of the silent clock. Its hands remain still, but perhaps that is closer to the truth of the universe than we realize. The stillness is not emptiness. It is fullness, complete and all-encompassing. The dance we perceive as time may be the shimmer of our awareness gliding across a frozen hole. In the chapters ahead, we will learn why scientists were forced to this conclusion, what it means for the way we think about beginnings and endings, and how, even in a timeless universe, the story of existence continues to astonish. Long before Einstein bent it and Wheeler tried to erase it, time was a simple, unquestioned backdrop to reality. In the 17th century, when Isaac Newton was laying the foundations of modern science, he gave the world a picture of time that seemed as solid and eternal as the laws of motion he discovered. For Newton, time was absolute. It ticked away at a steady pace, independent of the world it governed, flowing equably everywhere, unaffected by matter or energy. Time was the grand stage upon which the play of the cosmos unfolded, a stage that did not creak or bend, a stage that would endure even if no actors ever stepped upon it. This vision was powerful because it matched intuition. Humans already felt that time was universal. An hour in London was the same as an hour in Rome. A second in your life was the same as a second in the life of a distant king. When Newton declared this formally, it gave science a firm ground upon which to build. His mechanics, his laws of motion and gravitation, all required a uniform parameter to measure change. That parameter was time, flowing forward like a river whose current never falters. Objects accelerated, planets orbited, apples fell, and all these motions could be calculated with exquisite accuracy once time was treated as absolute. In Newton's framework, space and time were not tangled together. Space was a vast three-dimensional arena, infinitely stretching in all directions, ready to host the dance of bodies. Time was its twin backdrop, separate, one-dimensional, and eternal. The universe was like a giant clockwork machine, each cog turning with predictability, driven by forces that could be measured, mapped, and understood. The entire edifice of classical physics relied on the assumption that time was objective, a kind of divine metronome keeping rhythm for the cosmos. To imagine the Newtonian picture is to imagine a master clock hidden somewhere beyond the stars, ticking with perfect constancy. Every pendulum on Earth, every sundial, every pulse of a human heart was thought to be echoing this cosmic beat. No matter where you traveled, no matter how fast you moved, this universal rhythm would continue unperturbed. The cosmos itself seemed to move to its silent drum. This conception of time carried deep philosophical implications. If time is absolute, then every event in history has its fixed position, anchored in the grand sequence. Causes lead to effects, effects become causes, and the chain extends infinitely in both directions, into the past and into the future. For Newton, time did not need a beginning. It had always existed, and it would always exist. It was the eternal stage on which God's creation played out, a stage that could never crumble. Yet even in Newton's day, not everyone agreed. Thinkers like Leibniz argued that time was not an independent entity, but a measure of relations between events. To Leibniz, speaking of time without things happening in it was meaningless. But Newton held firm. He believed that even if nothing moved, even if the universe were empty, time would still flow, invisible and unstoppable. In his eyes, time was as real as the planets themselves, though untouchable and unseen. For centuries, this view dominated science and common sense alike. Navigators crossed oceans by the steady ticking of their chronometers. Astronomers predicted eclipses by calculating celestial mechanics with Newton's equations. Farmers measured the turning of seasons. Builders timed the swing of pendulums. And everyone trusted that an hour was an hour everywhere in the cosmos. The solidity of Newton's absolute time became part of the cultural fabric. But the Newtonian clockwork contained seeds of unease. If time is absolute, it must be the same for all observers. Yet, as telescopes improved and experiments grew more precise, subtle cracks began to appear in this assumption. The behavior of light did not seem to fit neatly into Newton's scheme. Maxwell's equations described electromagnetic waves with a fixed speed, but how could that speed remain constant in all reference frames if time itself was universal? The questions began to stir, though centuries would pass before they reached a breaking point. Looking back, Newton's absolute time feels both comforting and fragile. Comforting because it fits so naturally with experience. Our days seem measured by the same relentless tick. Our memories stack in linear order. Fragile because it depends on assuming a cosmic metronome that cannot be observed, only trusted. His framework worked astonishingly well for planets and pendulums, but when the 20th century arrived, the assumptions crumbled under the weight of new discoveries. Still, the legacy of Newton's time is enormous. It gave humanity confidence in the predictability of nature, the belief that with mathematics and careful measurement, the universe could be explained. It gave us the laws that guided the Industrial Revolution, that powered ships and factories, that mapped the heavens. Even when relativity shattered the notion of absoluteness, it did so only by standing on Newton's shoulders. To place yourself in Newton's world is to inhabit a cosmos of certainty. The heavens turn like gears, each moment flowing into the next in perfect order. There is no ambiguity, no relativity of experience, only the clean sweep of universal time carrying all things with it. Against this backdrop, human life feels both fleeting and secure. Fleeting because time is endless and we are small. Secure because the laws that govern everything are steady and impartial. Yet the stopped clock from our opening story whispers unease even here. If time were truly absolute, if its flow were guaranteed, why does physics today tell us otherwise? Newton's grand stage seems so natural, and yet, the deeper we look, the more it fades. It is as if the eternal river he imagined is only a mirage, one that dissolves as we move toward the realm of Einstein, where time bends and twists with space. The journey from Newton to Einstein is not merely a story of equations, but a transformation in how humanity conceives reality itself. Newton gave us a timeless backdrop, a comfortingly objective measure. Einstein would later tear that backdrop away and show us that time is not absolute at all, but relative, malleable, intertwined with the geometry of existence. From that moment onward, the very notion of time began to unravel, leading us step by step toward the radical vision of the Wheeler-DeWitt equation, in which the universal clock stops altogether. And so, as Newton's pendulums swing and his planets circle endlessly in our imagination, we prepare to follow the story further. From the eternal river, we shall move into a world where the flow is not steady but elastic, where seconds stretch and contract depending on how you move and where you stand. The age of relativity is approaching, and with it, the first cracks in the certainty of absolute time. For more than 2 centuries, Newton's picture of time ruled unchallenged. The universe was a stage where the seconds ticked uniformly, and everything else obeyed their rhythm. It was a comforting cosmos, reliable and predictable, like a vast clockwork wound up at creation. But at the dawn of the 20th century, this certainty began to unravel, not through grand philosophical speculation, but through stubborn experiments that refused to agree with Newton's script. At the center of this shift was a young man with wild hair and patient eyes, Albert Einstein, who would forever change the way we think of time. The cracks had been forming for decades. James Clerk Maxwell's equations of electromagnetism predicted that light traveled at a fixed speed, about 300,000 kilometers per second, regardless of its source. But if time and space were absolute, as Newton had insisted, how could this be true? If you were running toward a beam of light, shouldn't you measure it as moving faster? If you were running away, shouldn't you see it slower? According to Newton's framework, speeds must add and subtract, like trains on tracks. Yet no experiment could detect any difference in light's velocity. Light refused to obey Newton's common sense. The famous Michelson-Morley experiment of 1887 tried to catch light in the act, to detect the supposed ether through which it was thought to travel. The result was a null. No difference, no ether wind, no deviation from constancy. Light's speed appeared stubbornly the same, no matter how Earth moved in space. The cosmos was whispering that Newton's stage might be an illusion. Einstein, working quietly in a Swiss patent office in 1905, took these whispers seriously. He asked a bold question. What if the speed of light is indeed constant for all observers, and it is time and space themselves that must bend to make this true? In one stroke, he flipped Newton's eternal river upside down. Time was not absolute. It was relative, inseparably woven with space into a single four-dimensional fabric. This was the birth of special relativity. From Einstein's equations emerged consequences that sounded like science fiction. A moving clock does not tick at the same rate as a stationary one. A traveler moving close to the speed of light will experience time more slowly than those left behind. If you could journey at near light velocity and return, you might find centuries have passed on Earth while you have only aged a few years. Time dilation, it was called, and though at first it seemed absurd, experiments would later confirm it with exquisite precision. This relativity of time shattered the comfort of Newton's universal metronome. No longer could one speak of a single now stretching across the universe. The present for you is not the same as the present for someone racing past at a significant fraction of light speed. Simultaneity itself, once thought to be obvious, turned out to be relative. There was no cosmic stage keeping perfect time. Instead, each observer carried their own clock, their own measure of duration, tied to their state of motion. Einstein's insight did not stop there. A decade later, he extended relativity into the realm of gravity, producing the general theory of relativity. Here time bent not only with motion, but with the presence of mass and energy. Gravity, he proposed, was nothing more than the warping of space-time itself. The stronger the gravity, the slower time flows. A clock near the surface of Earth ticks ever so slightly more slowly than a clock on a mountaintop. A clock hovering near the edge of a black hole slows to a crawl, frozen from the viewpoint of a distant observer. The implications were staggering. Time was no longer a rigid background, but a dynamic participant in the universe. It curved, stretched, dilated, twisted in harmony with space. Reality itself was a malleable fabric, and time was one of its threads. Yet, Einstein's revolution, for all its strangeness, still preserved something essential. Time continued to exist. It was not erased, only made relative. Events could still be ordered, causes could still precede effects, though what precede meant depended on your frame of reference. Time was mutable but not absent, transformed but not annihilated. For many, Einstein's vision was exhilarating. The cosmos became more mysterious, more alive. Imagine standing at the edge of a black hole, where seconds stretch into infinities. Imagine racing among the stars, your heartbeat slowing relative to those at home. These were no longer fantasies but consequences of natural law. Humanity had cracked open the shell of Newton's certainty and found inside a universe far stranger, far more flexible. And yet, beneath the excitement, unease lingered. Relativity made time pliable, but it did not reconcile with the quantum world that was simultaneously unfolding. While Einstein was rewriting space and time, physicists like Planck, Bohr, and Heisenberg were uncovering the rules of the subatomic, where uncertainty ruled and particles behaved like waves. There, time still ticked like Newton's clock, a simple external parameter marching forward. Quantum theory required a backdrop of time to evolve probabilities, while relativity insisted that time was not fundamental but entangled with geometry. Two great theories, each beautiful, each accurate in its own domain, but fundamentally at odds. This contradiction would not be solved in Einstein's lifetime. He himself grew uneasy with quantum mechanics, refusing to accept its indeterminacy, its dice-throwing nature. He longed for a deeper order, a hidden unity. In his later years, he searched for a theory of everything, a single framework that would merge gravity and quantum physics into one. He did not succeed, but his questions would echo into the decades that followed, eventually leading to the haunting possibility that time itself might not belong in the ultimate description at all. It is worth pausing to feel the weight of Einstein's achievement. He took the most familiar thing in human experience, the steady march of seconds, and revealed it to be relative, elastic, dependent on motion and gravity. He showed that time could be stretched thin or thickened like honey, depending on where you stand in the cosmos. This was not only a triumph of intellect, but also a profound philosophical turning point. Humanity's place in the universe was no longer fixed. Even the flow of moments, the very heartbeat of existence, was revealed as perspectival. And yet, the clock had not yet stopped. In Einstein's world, it still ticked, albeit differently for each observer. There was still a sense of past, present, future, still a flowing river, even if it meandered and bent. The final blow to time as fundamental would come later, when others picked up Einstein's legacy and sought to fuse it with the quantum. In that fusion, the parameter of time would quietly vanish from the equations, leaving behind a universe that does not evolve at all. For now, though, imagine yourself in Einstein's universe. You hold a watch, and your friend far away holds one too. You know they may not agree, but each is true in its own frame. Time has become personal, relative, alive. The universal stage of Newton has collapsed, and in its place stands a flexible fabric. You are no longer an actor upon a rigid backdrop, but a thread woven into space-time itself, carried along by curves and motions. The revolution was complete, but it was only the beginning. As the 20th century unfolded, physicists would discover black holes and cosmic expansion, quantum indeterminacy and entanglement. Each discovery pushed harder on the seams of relativity and quantum mechanics, demanding a reconciliation. Out of that struggle would emerge the most radical idea yet, the Wheeler-DeWitt equation, in which the ticking of the clock ceases altogether, and the universe exists in timeless stillness. But before we arrive there, we must look at the places where Einstein's theory faltered, the cracks where gravity grew so strong and scales so small that relativity alone could not suffice. Einstein's vision of space-time was astonishingly successful. His equations could predict the orbit of Mercury more precisely than Newton ever could, explain the bending of starlight around the sun, and forecast the slow drift of galaxies in an expanding universe. It was a theory both elegant and profound, woven into the very geometry of reality. And yet, even the most brilliant ideas have boundaries, places where they collapse under their own weight. For Einstein, those boundaries appeared in the darkest corners of the cosmos, where gravity grew so extreme that space-time itself seemed to shatter. Consider the black hole. In Einstein's equations, if enough mass is packed into a small enough volume, space-time curves without limit, forming a region from which nothing, not even light, can escape. To a distant observer, time near the edge of this abyss slows and stretches, as though the seconds themselves are trapped by the immense pull of gravity. At the boundary, called the event horizon, clocks appear to freeze forever. If you were to watch a friend fall into a black hole, you would see them slowing down, their movements becoming sluggish, their image frozen at the brink. From their own perspective, however, they would fall through in finite time, crossing into a realm where the known laws of physics fail. Inside, Einstein's theory predicts a singularity, a point of infinite density where curvature becomes infinite and time itself ceases to make sense. But infinity is not a physical answer. It is a signal that the theory has broken down. Something deeper is needed, a framework that can handle both the vast scales of relativity and the tiny jittering scales of quantum mechanics. Without such a framework, black holes remain paradoxes, riddles at the heart of Einstein's legacy. The same breakdown appears when we turn our gaze backward to the origin of the universe. The equations of general relativity, when applied to the cosmos as a whole, suggest that everything we see today, the galaxies, the stars, the radiation between them, once emerged from an initial state of incredible density and heat. This is the Big Bang, the cosmic beginning. But push Einstein's equations all the way back, and they lead to a singularity, a point of zero size and infinite density, where time itself begins. Once again, the appearance of infinities tells us the equations cannot be the whole story. The Big Bang, like the black hole, is a place where Einstein's beautiful fabric tears apart. In both cases, the problem is the same. Relativity is a theory of the large, describing planets, stars, and galaxies with astonishing accuracy. Quantum mechanics is a theory of the small, describing electrons, photons, and atoms with equal precision. But neither can fully describe what happens where the large and the small collide, at the heart of a black hole or at the birth of the universe. At those extremes, the two theories clash, and time itself becomes uncertain. For Einstein, these singularities were troubling but unresolved puzzles. He suspected that a deeper theory was needed, one that could merge gravity and quantum mechanics into a seamless whole. But in his lifetime, no such theory emerged. He left us with two towering structures, each magnificent, each incomplete, standing on opposite sides of a gulf. For scientists who came after, the challenge was clear: bridge the gap. Find a framework in which the rules of the quantum and the rules of relativity coexist. Such a framework must be able to explain what happens when space-time is curved down to microscopic scales, when gravity becomes as strong as the quantum jitter of particles. Such a theory would be a theory of quantum gravity. The search for quantum gravity is not just about filling a gap in our equations. It is about understanding the true nature of reality itself. If Einstein's fabric of space-time tears apart at singularities, then perhaps space-time is not the final layer of the universe at all. Perhaps it is an approximation, a useful illusion that emerges only at large scales. Just as temperature emerges from the motion of countless particles, perhaps space and time themselves emerge from something deeper. This is where the story begins to bend toward the Wheeler-DeWitt equation, toward the shocking possibility that time itself is not fundamental. For if we attempt to write equations that combine quantum principles with the structure of the universe as a whole, we discover something strange. The parameter of time, so central to Newton and still present, though relative in Einstein, begins to disappear. To appreciate how radical this is, we must understand how deeply time was ingrained in science. Newton had treated it as absolute. Einstein made it relative but still real. Our daily lives insist upon it. Our memories, our plans, our aging, all depend on the flow of moments. Yet in the quest to describe black holes and the Big Bang, time itself seems to dissolve, slipping out of the equations like water escaping a broken vessel. The black hole, with its frozen horizons, hints at this dissolution. To the outside world, events at the horizon appear never to complete, time stretching into infinity. At the Big Bang, the very concept of before loses meaning, as if time has no foothold at all. These are not just curiosities, they are clues, pointing us toward a deeper truth about the nature of reality. And so, the stage is set. Newton's absolute time gave way to Einstein's relative space-time, which in turn reveals cracks at the edges of black holes and the birth of the cosmos. These cracks are invitations, beckoning us toward the next chapter of physics. To understand them, scientists like John Wheeler and Bryce DeWitt would dare to write an equation for the universe itself. In that equation, the ticking of the clock would vanish entirely, leaving us face to face with a timeless reality. But before we step into that abyss, let us linger at the brink of Einstein's limits. Picture the edge of a black hole, where light bends and time dilates, where the cosmos seems to hold its breath. Picture the first moments after the Big Bang, when the universe was smaller than an atom, seething with energy, where before and after had no meaning. These are places where our theories falter, but they are also places of profound beauty. They remind us that reality is stranger than any stage we have built for it, that time itself may not be what it seems. If relativity is the grand geometry of the cosmos, smooth and continuous, then quantum mechanics is its opposite, jittering, uncertain, alive with paradox. Where Einstein described planets bending space-time with elegant curves, the quantum world describes electrons flickering between possibilities, photons acting both like waves and particles, atoms existing in hazy clouds of probability. It is a universe not of certainties, but of chances, not of solid gears, but of shifting patterns. To step from relativity into quantum mechanics is like stepping from a cathedral of marble into a hall of mirrors, where every reflection bends and splits into multiple possibilities. The story begins at the turn of the 20th century, when experiments began to reveal cracks in the Newtonian picture of matter. Light, which had been thought of as a wave, sometimes behaved like discrete packets. photons. Electrons, thought of as tiny particles, sometimes behave like waves, spreading out and interfering with themselves. The universe seemed unwilling to choose between categories. At the smallest scales, it was both and neither. This dual nature was codified in the mathematics of quantum theory. Instead of definite positions and velocities, particles were described by wave functions, mathematical objects that told you the probabilities of finding them in different states. Until you measured them, they existed in superpositions, smeared across possibilities. Only when observed did they collapse into a definite outcome. The universe itself seemed to keep secrets, refusing to reveal them until pressed by an act of measurement. At the heart of this new world was uncertainty. Werner Heisenberg formalized it in his famous principle: you cannot know both the position and momentum of a particle with infinite precision. The more tightly you pin down one, the more the other slips through your grasp. This was not a failure of instruments, but a fundamental feature of reality. The microscopic world was not deterministic clockwork, but a shimmering fog of probabilities. Albert Einstein, who had himself helped launch quantum theory with his explanation of the photoelectric effect, grew uneasy with this new vision. He resisted the idea that nature at its core was indeterminate. God does not play dice, he remarked, skeptical that chance could rule the universe. But experiments sided with the dice. Again and again, quantum mechanics made predictions that matched observation with uncanny accuracy. Electrons tunneling through barriers, atoms absorbing discrete quanta of light, particles entangled across distances. All these phenomena, strange though they were, unfolded exactly as the equations foretold. And so, the quantum world established itself as the most successful theory of the small ever devised. It built the foundations of modern technology: semiconductors, lasers, nuclear energy, even the very computers used to simulate the equations themselves. Its accuracy was breathtaking, its consequences profound. Yet its picture of reality was unsettling. A universe of probabilities, where measurement brings reality into being, seems far removed from the solidity of everyday life. Within this framework, time still flowed in a familiar way. The Schrödinger equation, which governs the evolution of wave functions, included an explicit reference to time. The wave function changes as seconds tick forward, probabilities evolve, and systems shift from one configuration to another. In the quantum domain, time was a parameter, an external backdrop against which the dance of uncertainty unfolded. But here was the tension. Relativity had already told us that time is not an external backdrop, not absolute, not separate from the universe, but woven into space-time itself. Quantum mechanics still treated time like Newton had, as if it ticked away in the background, indifferent to the system being studied. Two theories, both correct in their own realms, but fundamentally incompatible. One bent time, the other ignored its bending. One dissolved simultaneity, the other depended on it. The clash becomes most apparent when we try to apply quantum mechanics not just to particles, but to the universe as a whole. For a single electron, you can treat time as external, supplied by the laboratory clock. But what is the clock when the system is the entire cosmos? If nothing exists outside the universe, where does time come from? To write down a wave function for the universe, you must confront this paradox. And when Wheeler and DeWitt attempted to do so, the time variable vanished. The Schrödinger equation, once dependent on t, became something else entirely: timeless. This is why quantum mechanics is not just another chapter in physics, but a pivot point in the story of time. It shows us that at the smallest scales, reality is probabilistic, relational, and slippery. It challenges our assumptions about determinism, about measurement, about what it even means for something to exist before we observe it. It forces us to question whether time itself might be like measurement, a relational phenomenon, something that emerges only in interaction, not something that sits waiting in the void. There is a strange beauty in this. Imagine a universe composed of shimmering possibilities, each moment a cloud of potential outcomes. Time, in this picture, is not the absolute river of Newton, nor the curved geometry of Einstein, but the rhythm by which probabilities change. Yet, if you strip away the external clock, the rhythm may vanish, leaving only a static wave function encompassing all possibilities at once. This is what the Wheeler-DeWitt equation suggests: that the ultimate quantum state of the cosmos is timeless, all at once, eternal. But we are not there yet. For now, we linger in the quantum hall of mirrors, marveling at particles that tunnel through barriers, at photons that interfere with themselves, at cats that are both alive and dead until we look. We marvel at entanglement, where two particles, separated by light years, share a single fate, as if distance is irrelevant. These are hints that our ordinary categories, space, time, causality, may not be fundamental, but emergent, fragile, context-bound. And yet, in daily life, we remain anchored in the flow of seconds. We glance at watches, grow older, remember yesterday, anticipate tomorrow. The quantum haze does not erase this experience. It underlies it, whispers beneath it. Like a faint second melody woven under the main theme, it unsettles without overwhelming. But when carried into the realms where relativity and gravity dominate, the quantum melody grows louder, clashing with the symphony of curved space-time, demanding a resolution. The stage is set for a confrontation. Relativity bends time, quantum mechanics ignores its bending, and both are true within their domains. At the edges of black holes, at the birth of the cosmos, neither is enough. The search for unity will force us to question whether time belongs in the fundamental equations at all. And so, from Newton's steady river to Einstein's pliable fabric, we now arrive at a universe of uncertainty, where the very notion of flow begins to shimmer. The clock still ticks, but faintly, uncertainly, as though preparing to vanish. By the middle of the 20th century, physics had reached a strange impasse. On one side stood general relativity, Einstein's masterpiece, a vision of the universe as a smooth fabric of space-time, bending gracefully under the weight of matter and energy. On the other side stood quantum mechanics, the unruly theory of the small, where particles flicker in and out of possibility, bound together by uncertainty and probability. Each theory was magnificent, each tested to exquisite precision in its own realm, and yet they seemed to speak entirely different languages. Like two monarchs ruling neighboring kingdoms, they coexisted uneasily, with borders that grew tense whenever one ventured too far into the territory of the other. Relativity was geometric, deterministic, continuous. It described the cosmos as a whole, from the slow dance of galaxies to the warping near a black hole. It treated space-time itself as real and malleable, flowing smoothly without jumps or breaks. Quantum mechanics, by contrast, was probabilistic, indeterminate, granular. It dealt with particles and fields, not with the whole of space-time, but with its contents. Time and relativity was a pliable dimension, woven into the fabric of the universe. Time in quantum mechanics was an external parameter, ticking away like Newton's metronome. The two views could not be reconciled, yet both were undeniably true. The tension became undeniable at the extremes. Consider the heart of a black hole. Relativity predicts a singularity, a point of infinite density where space-time collapses. Quantum mechanics insists that infinities are nonsense, that uncertainty and quantum fluctuations must smear out such extremes. At the birth of the universe, relativity again produces a singularity at the Big Bang, while quantum theory whispers that fluctuations, tunneling, and superposition might soften that edge. In both cases, the theories contradict one another, each failing to provide a complete picture. The problem at its core was time itself. In general relativity, time is part of the fabric, bent by mass, stretched by velocity, slowed by gravity. It is not external, but intrinsic. In quantum mechanics, time is simply a background parameter, unaffected by the processes it measures. When physicists tried to quantize gravity, tried to treat space-time itself with the same quantum rules as particles, they ran into a paradox. How do you apply quantum equations that depend on time to the very thing that defines time? How do you quantize the clock itself? The clash was not just mathematical, but philosophical. Relativity suggested a universe where the past, present, and future coexist within a four-dimensional block. Quantum mechanics suggested a universe where outcomes are not fixed until measured, where reality evolves probabilistically in time. One said all moments exist equally. The other said only probabilities of moments exist until the instant of measurement. Together, they painted an inconsistent picture, as if two portraits of the same person contradicted each other, one showing a smooth figure etched in stone, the other a blurred figure shimmering in possibility. Physicists gave this puzzle many names: the problem of quantum gravity, the problem of time, the search for unification. countless attempts have been made to bridge the divide. String theory, loop quantum gravity, causal sets, holographic principles. Each offers hints, glimpses, partial answers. But beneath them all lies the fundamental question: is time real, or is it an illusion that appears only when we look from a certain perspective? To appreciate the depth of the conflict, imagine trying to describe a black hole evaporating through Hawking radiation. According to quantum mechanics, particles can appear and disappear near the horizon, stealing energy from the black hole until it shrinks. But according to relativity, the horizon is a smooth surface. Time slows infinitely as you approach it, and no such particle games should be possible. To merge the two requires equations that respect both perspectives, and when those equations are written, time begins to slip away. This tension haunted Einstein himself. Though he pioneered relativity, he never accepted the full indeterminacy of quantum mechanics. He suspected there must be a deeper order, hidden variables that would restore determinism. Others, however, leaned into the uncertainty, embracing the idea that reality is fundamentally probabilistic. The philosophical divide was as wide as the mathematical one. Should the universe be deterministic, as relativity implied, or probabilistic, as quantum mechanics insisted? The clash over time sat at the heart of this debate. Some physicists compared the situation to a pair of maps. Relativity is like a globe, smooth and continuous, representing the whole world at once. Quantum mechanics is like a street map, granular, precise for small neighborhoods, but not for the entire globe. Each is correct in its own domain, but they cannot be overlaid without distortion. Somewhere, hidden beneath them, there must be a deeper map, one that explains why both partial pictures work where they do and why they fail where they overlap. The search for that deeper map brought physicists to daring proposals. Could space-time itself be emergent, like temperature or pressure, not fundamental but arising from deeper degrees of freedom? Could the ticking of time be an illusion, a convenient parameter we impose on a universe that is, in its essence, timeless? These questions were no longer philosophical speculation alone, but scientific necessities. Without them, the equations would not fit, the infinities would not vanish, the paradoxes would not resolve. It is in this context that John Wheeler and Bryce DeWitt attempted their bold construction. They sought to write down an equation that would describe the quantum state of the entire universe, folding gravity into quantum mechanics, uniting the small with the large. What they found was not a comfortable synthesis, but a shocking revelation. When you try to quantize the universe itself, time disappears from the equations. The Wheeler-DeWitt equation was born, and with it, the startling vision of a cosmos without time. But before we arrive at that radical step, it is worth pausing to feel the weight of the clash. Imagine standing between two colossal pillars. One is carved from smooth marble, shining with continuity, Einstein's relativity. The other is a shifting tower of glass, refracting into probabilities, quantum mechanics. Each is magnificent, yet they lean toward each other in contradiction, grinding at the point where they meet. You can hear the strain, the creaking of concepts under pressure, the collapse of certainty. Out of this tension, something new must be born. The next part of our story will follow Wheeler and DeWitt as they attempt to bridge the gap, to write the cosmic equation that unites the pillars. It is here that time itself will be stripped away, revealing a universe not of flowing moments, but of timeless being. And so, the stage is set. The river of Newton, the fabric of Einstein, the haze of quantum mechanics, all converge at a single equation that dares to erase the very notion of time. By the 1960s, physics stood at a crossroads. The two great pillars of modern science, general relativity and quantum mechanics, had both proven themselves in their domains. Relativity described the cosmos with sweeping grandeur, stars curving space-time, galaxies receding in the cosmic expansion, black holes lurking at the centers of galaxies. Quantum mechanics ruled the microscopic, electrons tunneling, atoms exchanging photons, radioactive particles decaying unpredictably. Each theory was dazzling, each had been tested and confirmed, and yet they refused to speak to one another. Like oil and water, they remained separate, shimmering but unmixed. Into this impasse stepped John Archibald Wheeler, a visionary physicist with a knack for seeing beyond the boundaries of conventional thought. Wheeler was a man of paradoxes, poetic in his language, yet rigorous in his science, imaginative enough to coin terms like black hole and wormhole, yet disciplined enough to train generations of physicists who would carry his legacy forward. For Wheeler, the challenge of unifying quantum mechanics and relativity was not merely technical, but existential. If these two pillars both described reality, then there must exist a deeper truth binding them. Alongside Wheeler came Bryce DeWitt, a more mathematically focused partner who shared Wheeler's determination to push past the contradictions. Together, they attempted something audacious, to write down the quantum equation for the universe itself, not just for a particle, not just for a field, but for everything, all matter, all energy, all space-time. This was no modest problem. It was the ultimate problem, the attempt to capture the whole cosmos in a single mathematical breath. The tool they used was the Hamiltonian formalism, a framework that allowed the energy of a system to define its evolution. In ordinary quantum mechanics, this formalism produces the Schrödinger equation, where the wave function evolves with respect to time. Wheeler and DeWitt asked, what if we applied the same logic to the gravitational field itself, to the very geometry of space-time? If we quantized gravity, treating space-time as a quantum object, what wave function would emerge? The result was both breathtaking and unsettling. The equation they derived looked superficially similar to Schrödinger's, yet one crucial piece was missing: the time derivative. The variable t, which had always been the parameter of evolution, was gone. The Wheeler-DeWitt equation contained no explicit reference to time at all. It was timeless. This absence was not a mistake, not a missing term that could be patched in. It was the natural outcome of trying to quantize the universe as a whole. In relativity, time is part of the geometry of space-time. It is not external, but intrinsic. When you promote space-time itself to a quantum object, there is no external clock against which to measure its evolution. The universe cannot sit inside a bigger cosmos with a ticking metronome. It must describe itself. And when it does, time vanishes. The implications were staggering. According to Wheeler-DeWitt, the universe is described by a wave function that does not evolve. It simply exists, eternal, containing within it all possible configurations of geometry and matter. There is no before and after, no past and future, no flowing river of moments. There is only the timeless whole. This vision was as radical as anything physics had ever proposed. Newton had given us absolute time, ticking everywhere. Einstein had made time relative, bending with gravity. Quantum mechanics had preserved time as a parameter, letting probabilities evolve. But Wheeler and DeWitt now propose something stranger, that at the deepest level, time does not exist at all. Not everyone knew what to make of it. Some saw the equation as a triumph, a glimpse of the long-sought theory of quantum gravity. Others dismissed it as incomplete, an artifact of the approach rather than a revelation about reality. But whether admired or doubted, it could not be ignored. It forced physicists to ask, if the fundamental description of the universe contains no time, why do we experience its flow so vividly? If reality is timeless, whence comes the ticking of clocks, the aging of bodies, the memory of yesterday? Wheeler himself was drawn to the philosophical depths of the problem. He spoke of the participatory universe, in which observers are not passive spectators, but active participants in bringing reality into being. Perhaps time itself, he suggested, emerges from the interplay between the quantum state of the cosmos and the conscious beings who measure it. Perhaps the flowing present is not fundamental, but relational, stitched from the interactions between parts of the whole. DeWitt, more cautious, focused on the mathematics. He explored how the Wheeler-DeWitt equation could be applied to cosmology, to describe possible shapes of the early universe, to hint at the origins of structure in the cosmos. He treated the timelessness not as philosophy, but as calculation, though the implications were never far away. Together, their work marked a turning point. For the first time, time itself had been banished from the most fundamental equation of physics. The stopped clock had become not just a metaphor, but a literal feature of the mathematics. And yet, paradoxically, this timeless wave function of the universe still contained within it the seeds of time as we know it. Patterns of entropy, correlations between subsystems, entanglement between degrees of freedom, These could all give rise to the illusion of flow, the emergence of a before and after. Just as temperature emerges from the random motion of molecules, so time might emerge from the structure of the universal wave function. It would not be fundamental, but emergent, not real in itself, but real enough for beings like us. To glimpse this possibility is to feel both awe and vertigo. Imagine the universe as a vast frozen sculpture, containing every possible configuration of space and matter. Within that sculpture are grooves and patterns that, when traced by consciousness, give the impression of motion. We, as beings embedded in the sculpture, feel the flow of time because our awareness moves along one of those grooves. But the sculpture itself does not move. It is timeless, complete, whole. The Wheeler-DeWitt equation remains notoriously difficult to solve. Even today, decades later, physicists wrestle with its mathematics, seeking clarity in its timeless form. Some use approximations, some embed it in larger theories like string theory or loop quantum gravity. None of these approaches has yet provided a final answer, but the boldness of Wheeler and DeWitt's dream remains. To write the equation for the universe, even if it tells us that time, the most familiar thing in human experience, is an illusion. And so, we stand at the threshold of a new vision. The river of Newton is gone. The pliable fabric of Einstein is gone. Even the probabilistic flow of Schrödinger is gone. What remains is a timeless wave function, silent and still. The question before us is how to reconcile this with the world we live in, where clocks tick and hearts beat, where we remember yesterday and hope for tomorrow. That reconciliation is the next step in our story, as we explore how time might re-emerge from timelessness, and how entropy and memory weave the illusion of flow from the stillness of the cosmic equation. When Wheeler and DeWitt stripped time from the equations of reality, what remained was not emptiness, but a vast mathematical object, the wave function of the universe. To hear that phrase is to feel both wonder and confusion. In ordinary quantum mechanics, a wave function describes the state of a particle or a system. It is a mathematical cloud of possibilities, telling us the chances of finding an electron here or there, of a photon traveling this way or that. But what could it mean to write a wave function not for a particle, not for a laboratory experiment, but for everything? What could it mean to describe the state of the entire cosmos in a single breath of mathematics? In the Wheeler-DeWitt picture, the wave function of the universe is timeless. It does not evolve according to some external clock, because there is no external clock. Instead, it encompasses all possible configurations of spacetime and matter simultaneously. Imagine a vast library where every possible book that could ever be written already exists. The wave function of the universe is something like that, except the books are entire universes, each with its own geometry, its own arrangement of stars and galaxies, its own histories. All possibilities coexist in the timeless architecture of this wave function. At first glance, such an idea feels impossible to connect with daily life. We feel time flow, we grow older, events happen in sequence. Yet, if the fundamental wave function is static, how can we account for this vivid sense of motion? Physicists who work with the Wheeler-DeWitt equation often answer that time, like temperature, is not fundamental but emergent. Just as no single water molecule has a temperature, but an ensemble of them does, so no single configuration of the universal wave function has a time. But when you zoom out and consider relationships between subsystems, an arrow of time can appear. Consider entropy, the measure of disorder. In a timeless wave function, there can still be correlations that make one state appear more ordered and another more disordered. When conscious observers like us trace paths through such correlations, we perceive change. We label the more ordered state the past, and the more disordered one the future. The experience of flow arises not from the whole being in motion, but from the way we slice it. The timeless sculpture contains grooves that we interpret as rivers. This picture is disorienting but not without precedent. Physicists are accustomed to emergent properties. Pressure, temperature, solidity, all are emergent. They do not exist at the level of individual particles. They arise from collective behavior. Time, in the Wheeler-DeWitt vision, may be another such property. Not fundamental, not built into the equations, but real enough for beings embedded within the wave function to experience. The mathematical expression of the wave function is almost impossibly complex. It must encode every possible shape of space-time itself, every possible way three-dimensional slices of the universe could be curved or connected. Each configuration is weighted by the wave function, much as a particle's position is weighted in ordinary quantum mechanics. To imagine it is like imagining an ocean of universes, each shimmering in possibility, overlapping and interfering. The Wheeler-DeWitt equation does not tell us which one is real. It tells us that the whole ensemble, the superposition of all of them, is reality. This leads naturally to questions that verge on the philosophical. If all possible universes exist in the wave function, are we simply one branch among many? Do we live inside a single classical history carved out of a deeper quantum whole? Some interpretations of quantum mechanics, such as the many worlds view, resonate with this vision, suggesting that every possible outcome of every quantum event continues in parallel, all contained in the universal wave function. Others take a more modest stance, arguing that the wave function is not literal reality, but a tool for calculating probabilities. Either way, the timelessness of the Wheeler-DeWitt equation forces us to rethink what it means for something to be real at all. Perhaps the most haunting aspect of the universal wave function is its stillness. In our everyday lives, change is everything. The sun rising, the seasons shifting, children growing. Yet here, at the foundation of physics, we are faced with a picture in which nothing changes. The universal wave function simply is. Motion, sequence, cause, and effect. These are patterns we infer from its structure, not properties it possesses in itself. To some, this seems like a betrayal of experience. To others, it is a profound invitation to humility, a reminder that the human perspective is not the cosmic perspective. One way to visualize this is to imagine a vast mural painted in infinite detail. To an outside observer, the mural is static, unchanging. Yet, if you were to step inside the painting to move from one patch of color to another, you might perceive a story unfolding. The mural itself does not change, but your path across it creates the illusion of narrative. In this analogy, the universal wave function is the mural, and our consciousness is the path. Time is the story we experience while moving across the stillness. Physicists wrestle with these ideas not just as philosophy, but as mathematics. They try to approximate the Wheeler-DeWitt equation in simplified mini-superspaces, where only a few degrees of freedom are considered, such as the scale of the universe's expansion. In these toy models, one can sometimes see time emerge approximately, as if it were hidden in the structure of the wave function and revealed only under certain conditions. The hope is that such insights can eventually be extended to the full equation, illuminating how our flowing time arises from the timeless whole. Still, even in its incomplete state, the concept of a universal wave function alters our perspective. It suggests that the cosmos is not a story unfolding, but a book already written in its entirety. We are characters reading through the pages, mistaking the order of the narrative for the flow of time itself. The book does not grow longer as we read. It was complete from the beginning. Our journey is simply the unfolding of our awareness across its chapters. In this vision, death does not erase existence, for the pages of one's life remain etched in the cosmic wave function. The past is not gone. It is eternally present. The future is not yet to be written. It is already there, waiting. This can be terrifying, as it strips away notions of choice and freedom. But it can also be comforting. Nothing is lost, nothing vanishes. Everything is preserved in the stillness of the whole. As we continue, we must ask, if the universe is truly timeless, how do we reconcile this with our most basic intuitions about cause and effect? If the wave function simply is, how can one event lead to another? How can there be a chain of causes? That question leads us deeper into the paradox, into the problem of the arrow of time, entropy, and the strange way order unravels into disorder. For within the timeless sculpture, we still perceive an irreversible flow. Understanding how that arrow arises will be our next step. If the Wheeler-DeWitt equation is to be taken seriously, then the most startling conclusion follows with quiet inevitability. The universe does not evolve. It does not pass from state to state, does not move from past to present to future. It simply exists, timeless, complete. What we call the flow of time is not written into the mathematics. It is not part of the foundation. It is a story that consciousness tells itself as it wanders across the structure of reality. This notion of a universe without time is profoundly disorienting. For all of human history, Time has been the thread that ties experience together. Memory links us to yesterday, anticipation pulls us toward tomorrow, and identity is woven through the continuity of moments. To suggest that time is not real, that it is an emergent illusion, feels like an assault on the very core of existence. And yet, when physicists follow the logic of relativity and quantum mechanics to their union, they find themselves staring into this abyss of timelessness. Imagine, for a moment, a film reel. On the strip of celluloid, every frame of a movie exists simultaneously. Nothing in the reel itself is moving. There is no inherent past or future, no flowing present. Only when the reel is played through a projector, one frame illuminated after another, does the illusion of motion appear. The Wheeler-DeWitt universe is like the film reel. All frames exist at once, side by side, written into the static structure of the wave function. Our minds are the projectors, giving us the sense of flow as we move through the frames. But the reel itself never changes. This image leads naturally to the idea of the block universe, a cosmos conceived as a four-dimensional structure in which every moment is equally real. In such a block, your birth, your present thoughts, and your eventual death all coexist, not as sequential events, but as neighboring regions of space-time. To you, embedded in the block, they seem to unfold in order. To the block itself, they are all present, unchanging. There is no becoming, only being. The absence of time at the fundamental level also dissolves the familiar categories of cause and effect. In a timeless cosmos, there is no before for causes to precede effects. Instead, there are correlations, patterns etched into the fabric. The striking thing is that those correlations mimic causality so well that we experience them as chains of cause and effect. We light a match and see a flame. We press a button and hear a sound. But beneath the experience lies only the static pattern, the timeless whole, in which both match and flame, button and sound are already present. Causality is the narrative we construct as we trace a path through the pattern. This does not mean that causality is meaningless. On the contrary, it is indispensable to creatures like us, whose survival depends on predicting outcomes, on learning from the past to shape the future. But from the perspective of the Wheeler-DeWitt equation, causality is like the rainbow, a phenomenon that appears real to observers but depends on perspective. Just as there is no thing in the sky that is the rainbow, only light, water, and an eye, so there may be no fundamental flow of time, only correlations and an observer weaving them into a story. There is, of course, resistance to this vision. Some physicists argue that time must be real, that it cannot be dismissed as illusion. They point to the irreversibility of processes, the second law of thermodynamics, the relentless growth of entropy. How could such an arrow emerge from a timeless whole? But others reply that this is precisely the point. Entropy and irreversibility may be emergent features, not foundations. The arrow of time could arise from the way subsystems interact, from the way we perceive correlations within the universal wave function. The whole may be timeless, but its parts can experience arrows. To live inside such a universe is to live inside a paradox. On the one hand, our most intimate experiences, aging, longing, remembering, are tied to the sense of time. On the other hand, the fundamental equations deny its existence. We are like actors improvising lines in a play that has already been written, unaware that the script exists all at once. We speak of tomorrow as though it is not yet real, but in the timeless block it is already inscribed, waiting for our awareness to arrive. Some find this terrifying. If the future is already real, where is freedom? If time does not flow, how can we choose? But others find comfort. If all moments are eternally present, then nothing is ever lost. The laughter of a child, the warmth of a summer afternoon, the glow of a distant star. These are not swallowed by time, but preserved forever in the structure of reality. Death itself becomes less final, for one's moments remain as real as any other. The challenge is that we cannot step outside the block to see it whole. We are embedded within it, bound to the illusion of flow. Our minds, with their fragile memories and anticipations, carve order out of timelessness. We cling to clocks and calendars, building civilizations around their tick and turn, unaware that beneath them lies only stillness. The Wheeler-DeWitt equation does not answer every question. It is notoriously difficult to solve, and its full implications remain unclear. Some interpretations suggest that time is hidden, that it reappears in certain approximations, that what is lost in the whole can be regained in the parts. Others suggest that time is fundamentally gone, that its absence is not a flaw, but a revelation. The debate continues, unresolved. But whether time is emergent or fundamental, whether the wave function is a literal object or a mathematical tool, the vision it offers is inescapably profound. It invites us to reimagine our place in the cosmos, not as travelers carried forward by a river of time, but as beings tracing paths through a timeless structure, not as creatures caught in a flow, but as readers moving through the pages of an eternal book. To picture this is to return once again to the image of the stopped clock. Its hands are frozen, yet the world continues. Perhaps the truth is that the world itself is frozen too, and only our awareness is moving, creating the illusion of change. Perhaps time, the most intimate of experiences, is the grandest of illusions, conjured by a timeless cosmos. And yet, paradoxically, it is precisely this illusion that gives life meaning. Without time, there is no story, no growth, no love, or loss. Even if time is not fundamental, it remains real enough for us. Like the rainbow, it may be an artifact of perspective, but it colors our existence. We cannot step outside it, nor would we wish to. In the chapters to come, we will explore how this arrow of time arises from timelessness, how entropy and memory weave the illusion of flow, and how modern physicists like Carlo Rovelli attempt to make sense of a cosmos where time is not fundamental. For if we live in a universe without time, then understanding how we feel its passage is one of the deepest mysteries of all. If the Wheeler-DeWitt equation tells us that the universe is timeless, a still wave function containing all possibilities at once, then why do we so stubbornly feel the flow of moments? Why does life unfold as a story rather than as a frozen sculpture? The answer, many physicists believe, lies in the concept of entropy, the measure of disorder, the great director of time's arrow. Entropy was born in the 19th century out of the study of heat engines and steam. Scientists like Clausius and Boltzmann sought to understand why energy always seemed to run downhill, why machines lost efficiency, why heat flowed from hot to cold, but never the other way around. They discovered that in any closed system, the amount of disorder tends to increase. This principle became the second law of thermodynamics. Entropy always rises. At first glance, entropy is a simple bookkeeping rule. If you pour cream into coffee, it mixes. If you shatter a glass, it does not leap back together. If you leave a warm cup on a table, it cools rather than heating itself. These processes are irreversible. You can imagine them going the other way, but you never see it happen. Entropy is the reason why. Systems move toward states of greater disorder because those states are far more numerous. To see this, imagine shuffling a deck of cards. There are countless possible arrangements, but only a few look ordered to human eyes. Say, all the suits aligned or the numbers in sequence. If you shuffle randomly, the odds overwhelmingly favor a messy arrangement. In the same way, the universe is vastly more likely to drift into disorder than into order. Entropy is the mathematics of that likelihood. And here lies the profound connection to time. Entropy gives direction to experience. The future is the direction in which entropy increases. The past is the direction in which it was lower. Our memories work because the brain, like every other system, leaves traces as entropy rises. Eggs break, but broken eggs do not unbreak. Ice melts, but melted water does not refreeze spontaneously. Each irreversible change is a signpost pointing from past to future. Without entropy, time would have no arrow. This is striking because the fundamental laws of physics, Newton's, Einstein's, Schrödinger's, are, in principle, reversible. Run the equations backward and they still hold. Nothing in the mathematics forbids a broken egg from reassembling or a film reel from running in reverse. Yet, in reality, we never see such reversals. Entropy explains the gap between law and experience. It is not the equations that give us time's arrow, but the overwhelming statistical tendency toward disorder. In the timeless universe of Wheeler-DeWitt, entropy may be the key to why we perceive time. The universal wave function itself does not evolve, but within it are patterns of low and high entropy. Conscious beings, embedded in such a structure, experience correlations that align with entropy's direction. We live inside the groove where entropy increases, and so we feel the flow of time. It is not that time moves forward, it is that we move through configurations of rising entropy and mistake the sequence for motion. Think again of the frozen mural, the timeless painting of all possibilities. Entropy is like the shading of that painting, darker in some regions, lighter in others, forming gradients. As our awareness traces a path across the mural, we follow those gradients, and it feels like the story is unfolding. The painting is still, but the shading tricks us into perceiving direction. Entropy also explains why the past feels fixed while the future feels open. The past has lower entropy, with records and memories that preserve its traces. The future, being higher entropy, has countless possible outcomes. From our perspective, the past is written and the future unwritten. But in the timeless wave function, both are equally present. Entropy is what divides them, what convinces us that one is behind us and the other ahead. There is, however, a puzzle. If entropy always increases, it must have been low at some point. Why was the early universe so ordered? The Big Bang, far from being a chaotic explosion, appears to have been astonishingly low in entropy. The smoothness of the cosmic microwave background, the near-uniform distribution of matter, these are signs of an extraordinarily special initial condition. Why the universe began in such an improbable state is one of the great mysteries of cosmology. Without that low entropy beginning, we would not have the arrow of time we experience. Some physicists speculate that this initial low entropy may be a clue to deeper laws, perhaps tied to quantum gravity, or to the very structure of the universal wave function. Others suggest that it is simply a brute fact, one of those things we must accept without explanation. Either way, it is the foundation of our temporal experience. Without that improbable beginning, there would be no flow, no history, no memory, no narrative. Entropy also connects with human life in intimate ways. We age because our bodies, though complex, cannot escape the second law. Our cells accumulate damage, our order dissolves into disorder. Our civilizations rise and fall in tandem with energy flows, consuming low-entropy resources and producing high-entropy waste. Even thought itself leaves a trail of entropy, as neural firings dissipate energy. To be alive is to ride the arrow of entropy forward. In this sense, entropy is both the destroyer and the storyteller. It robs us of youth, but it gives us history. It erodes mountains, but it paints landscapes. It pulls stars toward collapse, but it carves galaxies into beauty. Without entropy, there would be no arrow, no experience of time, only the stillness of the wave function. With entropy, we gain the illusion of flow, the bittersweet passage that defines existence. And so, entropy is the bridge between the timeless whole and our temporal lives. The Wheeler-DeWitt equation may describe a frozen cosmos, but entropy explains why, inside that cosmos, creatures like us perceive direction. Time, in this view, is not fundamental but emergent. It is born from disorder, sculpted by improbability, written in the decay of order. The paradox is poignant. The very thing that gives us time also guarantees our mortality. Entropy's arrow moves only one way, toward greater disorder, toward heat death, toward the fading of distinctions. It grants us the narrative of life, but it ensures that all stories must end. Perhaps that is why the illusion of time feels so real, so undeniable, because without it, there would be no story to tell, and with it, we are carried toward endings we cannot escape. In the chapters to come, we will explore how this arrow is not only physical, but also psychological. Memory, perception, consciousness itself, all are tied to entropy. If the universe is timeless, then our experience of time must be an emergent trick of the mind, woven out of entropy's patterns. To understand this is to move closer to the truth of who we are in a cosmos where the clock does not tick, but where we still feel its echo. If entropy gives the universe its arrow, then consciousness is the lantern that lights that arrow for us, turning correlations and disorder into the lived feeling of past, present, and future. The Wheeler-DeWitt equation may be timeless, but the human brain does not experience timelessness. Instead, it weaves the illusion of flow, stitching together fragments of memory and sensation into the seamless narrative we call time. The brain is, at its core, a physical system bound by the same laws as everything else. Neurons fire, chemicals diffuse, patterns of electrical activity ripple across networks. Each of these processes leaves traces. Each consumes energy. Each adds to entropy. In doing so, the brain constructs records, faint imprints of past states, that allow us to distinguish before from after. Without these records, there would be no memory, no continuity, no sense of having moved through time at all. Think of a photograph. It is a frozen imprint of a moment. By itself, it is timeless, a still slice of the wave function. But place it in an album with others, and suddenly a story emerges. A child grows, a family gathers, a landscape changes. The brain works the same way. It stores imprints of experiences, memories, which it then orders and interprets. The flow of time is not in the universe, but in the sequencing of those imprints. Modern neuroscience suggests that the hippocampus plays a central role in this sequencing. It binds together perceptions into episodes, situating events in an order that becomes the skeleton of our personal history. When the hippocampus is damaged, memory collapses, and with it, the sense of continuity. Patients may live perpetually in the present, unable to string moments into a flow. This tragic condition is also revealing. It shows how fragile time is as an experience, how dependent it is on the architecture of the mind. But memory alone is not enough. Consciousness also projects forward, anticipating what is to come. The brain does not passively record the past. It constantly predicts, creating models of the near future so that we can act in time to survive. When you reach for a cup, when you cross a street, when you speak a sentence, your brain is already calculating milliseconds ahead, preparing for what comes next. This predictive machinery reinforces the illusion of flow, as if we are moving along a line from remembered past to anticipated future. In this way, consciousness is like a weaver at a loom. On one side lie the threads of memory, on the other, the threads of anticipation. And in the middle is the narrow strip we call the present moment. The brain shuttles back and forth, tying past to future, creating a continuous fabric. The now is never static, but always a seam in the weaving. Psychologists studying perception of time have discovered that even the present is an illusion stretched in both directions. We do not experience the world instant by instant, but in windows of integration. Roughly every few dozen milliseconds, the brain collects sensory input, binds it into a coherent picture, and presents it to consciousness. The now you feel is already a construction, a stitched bundle of slightly older signals. In effect, you are always living a fraction of a second in the past, catching up to events that have already happened. This creates a haunting echo with the Wheeler-DeWitt vision. Just as the universal wave function is timeless and our sense of flow arises from the way we slice it, so too is the brain receiving timeless signals and stitching them into a flowing narrative. The illusion of time appears at both the cosmic scale and the neural scale. It is the same story written twice, once in mathematics, once in biology. The connection deepens when we consider dreams. In dreams, time becomes elastic, expanding and contracting unpredictably. Hours of dream narrative can occur in seconds of real time. Sometimes events repeat, sometimes they dissolve into each other without sequence. This reveals that the brain can construct the sense of time in arbitrary ways, untethered from physical clocks. If the brain can bend time in dreams, perhaps waking life is also a construction, one shaped by memory and entropy, but not guaranteed by physics. Philosophers have long wondered whether the flow of time is real or only phenomenological. Augustine confessed in his Confessions that he knew what time was until someone asked him to define it. In the modern age, physics has only deepened the mystery, showing that time may not exist fundamentally, even as consciousness insists on its passage. We are caught between equations that deny time and experiences that depend on it. There is also the puzzle of free will. If all moments are equally real in the timeless block universe, then our choices may be as fixed as the grooves in a sculpture. Yet we feel as though we choose, as though we carve the future from the clay of possibility. Some suggest that free will, like time, is an emergent phenomenon, a story told by consciousness to make sense of behavior. Others hold out hope that the mind can generate novelty even within a timeless structure, that our awareness participates in selecting a path through the wave function. Either way, consciousness and time are inseparable for us. Without the illusion of flow, we could not act, remember, or love. Life would collapse into stillness. The irony is that physics suggests stillness is what reality truly is. The brain, then, is a magician, conjuring motion from stillness, projecting a river onto a frozen mural, and we, enchanted by the trick, call the river life. Perhaps this explains why time feels both intimate and elusive. It is not merely a physical parameter, but the very medium of consciousness. It is the rhythm of memory and anticipation, the heartbeat of awareness. It is the lens through which we see the timeless cosmos. Even if time is not fundamental, it is fundamental to us. In this way, the Wheeler-DeWitt equation and the neuroscience of memory converge. Both tell us that time is not in the foundations. Both tell us that flow is an illusion. And yet, both show us that the illusion is indispensable, that it arises naturally from the way complex systems, whether universes or brains, organize themselves. The illusion may not be true, but it is real enough to live in. As we move forward, the next question becomes, if time is emergent, how exactly does it emerge? How do entropy and entanglement conspire to give us arrows and flows within a timeless structure? To explore this, we must turn to modern voices like Carlo Rovelli, who has argued with poetic conviction that time is not fundamental but relational, that it arises only in the links between systems. His vision offers one of the most compelling ways to reconcile timeless physics with temporal experience. Among the physicists grappling with the strange possibility of a timeless universe, few voices have been as eloquent and insistent as Carlo Rovelli. A pioneer of loop quantum gravity, Rovelli is both a scientist and a philosopher, a writer who weaves equations with metaphors, giving readers a glimpse of a cosmos where time is not the backbone, but an illusion stitched from relationships. For Rovelli, time is not something that exists independently. It is not a container, not a river, not a universal ticking metronome. Instead, it is a network of relations among events, an emergent quality that arises only when systems interact. In his vision, the Wheeler-DeWitt equation's timelessness is not a problem, but a clue. It is telling us that the universe does not possess time at the deepest level. Time appears only when we look at subsystems, when we describe one part of the universe in relation to another. Just as temperature is meaningless for a single molecule, but meaningful for a collection, time is meaningless for the entire universe, but meaningful for interactions within it. Loop quantum gravity, the field Rovelli helped create, is one of the major contenders for a theory of quantum gravity. Unlike string theory, which imagines tiny vibrating strings underlying matter and space, loop quantum gravity imagines that space-time itself is quantized. Instead of being continuous, smooth fabric, space is woven from tiny loops of quantum fields, like threads in a tapestry. At the smallest scales, space-time becomes granular, a network of discrete relations rather than an unbroken continuum. In such a picture, time cannot be fundamental, because nothing is evolving against an external clock. The loops are not ticking, they are relations, static in themselves. What we call time emerges when we compare one subsystem to another, when we describe how one pattern changes relative to another. The ticking of a clock, the orbit of a planet, the beating of a heart, these are not reflections of universal time, but correlations between subsystems. Rovelli often invokes a simple analogy. Imagine describing the motion of a pendulum without reference to time. You could say, the pendulum is at its lowest point when the spring is most compressed, or the pendulum passes through the center when the attached gear shows a certain angle. In this description, there is no time variable, only correlations between events. For Rovelli, this is how the universe works at the deepest level. Time is nothing more than the ordering of correlations. This relational view explains why the Wheeler-DeWitt equation contains no time. If you are writing the wave function of the whole universe, there is nothing outside it to serve as a clock. But within the universe, relations abound. Subsystems evolve relative to each other, and these relative changes give rise to what we perceive as temporal flow. It is not that time is fundamental, it is that change is. Time is our shorthand for change. This vision carries deep philosophical implications. If time is not fundamental, then the present moment is not a special slice of reality. The flow we feel is the brain interpreting correlations, not the universe moving. Rovelli goes further. The distinction between past and future is also emergent. It arises from entropy and the way we, as subsystems, interact with the world. To a sufficiently detached observer, if such a thing could exist, the universe would appear as a static web of relations with no privileged direction. Some find this disorienting, even despairing, but Rovelli himself speaks of it with wonder. In his writings, he describes time not as a loss, but as a gift. To see it as emergent is to free ourselves from the illusion of permanence, to recognize the fragility and beauty of each moment. If time is not fundamental, then our experience of it is all the more precious, a delicate construction of mind and relation. Fragile as a soap bubble, the relational view also opens new avenues for physics. If time is not fundamental, then the problem of reconciling relativity and quantum mechanics shifts. Instead of trying to force time into the equations, we can look for patterns of correlation that generate the experience of time. In loop quantum gravity, these correlations are woven into the spin networks and spin foams that represent space-time at the smallest scales. Change is real, but it is not the march of a universal clock. It is the shifting of patterns in relation to one another. Ravelli sometimes describes the universe as a grand conversation. Each particle, each field, each subsystem speaks to the others in terms of correlation. What we call time is simply the grammar of this conversation, the way events are related. There is no master of ceremonies, no ticking clock overseeing the dialogue. There is only the endless interplay of voices, weaving the fabric of reality. This vision resonates with certain strands of philosophy, and even with aspects of Eastern thought, where time is not always conceived as linear or fundamental. Instead of being a rigid framework, it is a mode of perception, a way of experiencing change. Ravelli's science does not borrow from these traditions, but it converges with them, suggesting that our most basic intuitions about time may be cultural illusions, not cosmic truths. Yet, for all its elegance, the relational view does not erase the mystery. If time is emergent, why does entropy give it such a compelling arrow? If the universal wave function is timeless, why does consciousness so vividly experience flow? Ravelli's framework offers a path forward, but the questions remain profound. Perhaps they always will. Still, the relational view offers something rare in modern physics, a vision that is not only mathematically compelling, but also philosophically nourishing. It tells us that the cosmos is not a machine running on an invisible clock, but a network of relationships, alive with possibility. It tells us that time is not a prison, but a perspective. It tells us that the flow we feel, though illusory, is no less real for being emergent, for it is the medium in which we live and love. And so, in the timeless stillness of Wheeler DeWitt, Ravelli hears not silence, but dialogue. The absence of a universal clock is not emptiness, but fullness, a web of correlations richer than any single arrow of time could capture. Our experience of time is the song we hear as we move through that web, a song composed of relations, entropy, and consciousness. It may not be fundamental, but it is ours. As we continue, we must confront the deeper consequences of a block universe where past, present, and future coexist. If time is relational, if the arrow is emergent, then what does it mean for cause and effect? What does it mean for freedom, for choice, for the very notion of history? To live in a timeless cosmos is to live in a paradox, one we will explore in the chapters ahead. If time is not fundamental, if the Wheeler DeWitt equation whispers that the universe is timeless and Ravelli reminds us that what we call time is only relationships, then one vision begins to emerge with startling clarity: the block universe. In this picture, the cosmos is not a river carrying us from past to future. It is not a story being written as we go. It is a block, a four-dimensional structure in which all events, past, present, and future, exist together, equally real, eternally present. To imagine this, return to the metaphor of the film reel. Every frame exists simultaneously on the strip. The entire story is contained in the reel itself. What we call the movie is only our perception of the frames projected one after another. The reel is the block universe, static and complete. Our consciousness is the projector, lighting up one frame at a time, giving us the sensation of motion. But the reel itself does not move. In the block universe, your first breath, your last breath, and this present thought all coexist. They are not erased, not waiting, not passing. They are coordinates in the structure, like streets in a city. To you, walking through the city, they appear in sequence. But from the perspective of the city itself, all streets exist at once. The notion of now is not cosmic but parochial, a local slice defined by your position and motion. Einstein himself leaned toward this view. In a letter of condolence to the widow of his friend Michel Besso, he wrote that for physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. To Einstein, the block universe was not speculative philosophy, but a natural implication of relativity. If simultaneity is relative, if what is now for me is future for you, then no single present can be universal. All moments must coexist, equally real. This vision unsettles our everyday understanding of life. We live as though the past is gone, the future is not yet real, and only the present has existence. The block universe denies this. It tells us that the past is not lost and the future is not open. Everything simply is, etched into the four-dimensional structure. Our feeling of moving from one moment to another is perspective, not physics. The block universe also reshapes our notion of causality. In ordinary language, causes precede effects. A seed causes a tree, a spark causes a fire. But in a block, nothing precedes anything else. All correlations are already there, woven into the structure. The seed and the tree coexist, as do the spark and the fire. Causality becomes a way of reading the block, not a process that unfolds. It is our brain's narrative, not the universe's mechanism. This can feel like a loss. Where, then, is freedom? If your tomorrow is already real, how can you change it? If your life is etched into the block, how can you say you are choosing at all? Yet some philosophers suggest that freedom is compatible with the block. To choose is to be the kind of being whose path through the block includes deliberation, hesitation, and decision. The choice is not made outside the block, it is part of the block. You are still responsible, because your nature and your actions are etched together. Others find comfort in the block universe. If all moments coexist, then nothing is truly lost. The laughter of a child, the glow of a sunset, the warmth of a hand in yours, these are not swallowed by the past, but preserved eternally in the structure. Death itself becomes less final, for the moments of a life do not vanish. They remain as real as any others, part of the block, permanent as streets in the city of space-time. The block universe also reframes cosmology. In relativity, the expansion of the universe is not galaxies flying apart in time, but the geometry of the block itself. The Big Bang is not long ago, but a region of the block. The future heat death is another region. The cosmos is not evolving, it is laid out. We are simply moving through its coordinates, experiencing slices of its architecture. Still, unease lingers. The block universe feels cold, impersonal, stripping away the vividness of becoming. In our lives, the thrill is in the unfolding, the uncertainty of what comes next, the hope and fear of futures not yet written. To be told that the future is already there, already real, can feel like a betrayal of that thrill. It replaces the drama of becoming with the stillness of being. But perhaps the truth lies in the paradox itself. The block universe may be the cosmic perspective, while the flow of time is the human one. Both are real, but at different levels. The block is the sculpture. The flow is the way we walk through it. One is timeless, the other experiential. To dismiss either is to miss the fullness of reality. Physicists still debate whether the block universe is the final word. Some argue that quantum indeterminacy suggests genuine openness in the future, that not all of the block is written. Others insist that even quantum randomness must be part of the block, each outcome etched into branching structures. The debate remains unresolved, but the Wheeler-DeWitt equation tilts strongly toward timelessness, making the block universe a natural companion to its vision. And so, we are left with a haunting image, the cosmos as a vast eternal architecture where all moments coexist. Our lives are not fleeting sparks in the dark, but eternal patterns, preserved in the structure. The flow of time is not real in itself, but neither is it meaningless. It is the way finite beings, moving through the block, experience what is already there. The block universe changes how we think about memory, death, choice, and meaning. It challenges our intuitions but offers a strange kind of solace. Nothing is ever lost, everything is written. Yet it also raises new questions. If all moments coexist, why do we feel motion? Why do we remember the past but not the future? Why does entropy point one way and not the other? To answer these, we must return to the idea of cause and effect, and how they survive, or dissolve, in a timeless cosmos. For if the block is real, then causality itself must be reimagined. That will be our next step, as we explore what it means to speak of causes and consequences when nothing truly unfolds. Cause and effect are among the deepest habits of thought. We grow up with them, live by them, and build our science on their foundation. The sun rises because the earth turns. A tree falls because the wind pushes. A glass shatters because it slips from the hand. To speak of the world without cause and effect feels impossible, like trying to imagine language without grammar. Yet, in a timeless cosmos, one in which all events coexist in the block, the sequence of causes leading to effects dissolves. The universe contains correlations, not chains. In a block universe, the spark and the fire exist together. The match does not precede the flame. Both are coordinates in space-time. The human mind, walking through the block, perceives one as earlier, the other as later, and stitches them into a narrative. But from the cosmic perspective, there is no before and after. The spark and the flame simply are. Causality is the way we read the pattern, not the way the universe writes it. This is profoundly unsettling. If causes do not generate effects, what becomes of science itself? Physics has thrived by predicting what follows from what. Strike this, and that will move. Heat this, and it will expand. The success of science is measured in its ability to capture causality in equations. But if the block universe is real, then science may not be describing causes at all. It may be describing correlations, timeless relationships written into the fabric. Take, for example, Newton's second law: force causes acceleration. In a timeless perspective, this is not cause and effect, but correlation. Whenever a force vector of a certain magnitude is present, an acceleration of a corresponding magnitude is also present. The law is a pattern in the block, not a chain in time. To us, embedded within the block, the pattern looks like cause and effect. But that is a perspective illusion, not a cosmic truth. This idea has long echoes in philosophy. David Hume, centuries before relativity or quantum theory, argued that causality is not something we see directly in the world. What we see are sequences of events, A followed by B, and from repeated observation, we infer a connection. Hume insisted that causality is not given in perception, but imposed by the mind. Modern physics, with its block universe, seems to confirm Hume's skepticism. The mind sees order and assigns arrows, but in the cosmos itself, there are only correlations. Still, the illusion of causality is indispensable. We cannot live without it. Our survival depends on anticipating consequences, on believing that fire burns because heat causes pain, that eating sustains because food causes strength. If we attempted to live by the block's perspective, treating all events as simultaneous, we would be paralyzed. The brain insists on cause and effect because it must, because organisms that perceive the world in such terms survived long enough to pass on their genes. The illusion is evolution's gift, a fiction that works. But even within physics, causality has proven flexible. In quantum mechanics, entangled particles defy classical causality. A measurement here seems instantly correlated with a measurement light years away, without any cause traveling between them. Some interpret this as spooky action at a distance. Others see it as evidence that causality is not fundamental, that entanglement correlations are simply timeless features of the wave function. In relativity, too, causality bends. Simultaneity becomes relative, and what counts as a cause in one frame may be an effect in another. The strict chain of "this leads to that" phrase under scrutiny. The Wheeler-DeWitt equation deepens the challenge. With no time parameter, there is no sense in which one event produces another. There is only the static wave function, encoding all possible states. What we call causality is the way subsystems appear when compared. Within the timeless whole, there is no universal arrow of cause. There are only local arrows, emerging from entropy and correlation, valid for us, but not for the cosmos. To grasp this, imagine a tapestry. From a distance you see figures. A hunter with a bow, an arrow flying, a deer struck. The story is clear, cause and effect. But step closer, and you see only threads woven together in a pattern. The hunter, the arrow, the deer are not events unfolding but arrangements coexisting. The story is in your eye, not in the threads. The universe, too, may be a tapestry. Causality is the picture we perceive, not the fabric itself. This does not mean science is wrong. On the contrary, it explains why science works so well. The correlations in the block are stable and precise, so our illusion of cause and effect maps onto them with uncanny reliability. Laws of nature are not descriptions of causes, but of patterns, timeless truths about the structure. When we use them to predict, we are not invoking chains of causality, but navigating the block along its correlations. The predictions succeed because the block is consistent, not because time flows. The implications for free will are profound. If causality is an illusion, then our choices are not causes of future events, but part of the block itself. Your decision to raise a hand, your future action of raising it, both coexist in the timeless structure. From within, you feel the choice causing the motion. From the cosmic perspective, both are coordinates. The choice is real, but it is not a cause. It is part of the eternal arrangement. This realization can feel deflating, even fatalistic. If all is written, if causes do not generate effects, what room is there for meaning? But one might also see it differently. If all moments coexist, then your life is not a fragile thread unraveling, but an eternal pattern, forever present in the block. Meaning does not come from creating the future, but from being part of the timeless whole. Your choices are still yours, not because they change what comes next, but because they are etched into the structure that is you. In the end, causality may be like time itself, an illusion indispensable for life, but not fundamental. We live by it, depend on it, and would be lost without it. But the cosmos does not need it. The block is complete without causes or effects. It is we who add arrows and chains because our minds demand them. The universe offers patterns. We weave them into stories. And so, from Newton's clear causes to Einstein's bent arrows, from quantum indeterminacy to Wheeler-DeWitt timelessness, causality itself dissolves. What remains is the web of correlations, the eternal fabric. In the chapters to come, we will explore how physics wrestles with this dissolution, how mathematicians struggle with equations that lack time, and how human beings search for meaning in a cosmos where neither time nor causality is fundamental. The Wheeler-DeWitt equation is elegant in conception, but brutal in practice. On paper, it seems to hold the promise of unifying relativity and quantum mechanics, capturing the entire universe in a single mathematical expression. But as soon as physicists try to work with it, they encounter walls of difficulty so steep that decades of effort have yet to scale them. The equation is not only hard to solve, it is hard to even interpret. Its timelessness, so profound in philosophy, is also a practical obstacle in physics. To understand the difficulty, one must recall what the equation is trying to do. In ordinary quantum mechanics, the Schrödinger equation describes the evolution of a system's wave function over time. You input a wave function at one moment, apply the Hamiltonian, the operator representing the system's energy, and the equation tells you what the wave function will look like later. It is a recipe for prediction. Time is the thread that stitches initial conditions to future states. The Wheeler-DeWitt equation, by contrast, has no time parameter. It does not evolve. Instead, it demands a wave function that satisfies a static condition. The Hamiltonian applied to the universe's wave function must equal 0. This is already strange, for it suggests a frozen wave function, one that simply exists rather than unfolds. But it also means that the familiar tools of quantum mechanics, prediction, evolution, initial states, lose their meaning. How do you calculate a future when there is no time for it to occur in? Mathematically, the equation is fearsome. It must account for every possible configuration of space-time geometry, every way three-dimensional slices of the universe can be shaped. Each configuration is a point in what physicists call superspace, an unimaginably vast space of all possible spatial geometries. The wave function of the universe must live in this superspace, assigning amplitudes to every possible geometry. But superspace is not only vast, it is riddled with infinities. To navigate it is to walk through a labyrinth without walls or landmarks. Physicists often try to simplify by considering mini-superspace models, reducing the problem to a few degrees of freedom, such as the overall size of the universe. In these toy models, the Wheeler-DeWitt equation sometimes yields solvable forms, and one can glimpse how time might re-emerge approximately. But these models are crude, leaving out the richness of real geometry. They are like studying biology by looking only at a single cell, useful, but not the whole organism. Another challenge is the interpretation of probability. In ordinary quantum mechanics, the wave function gives probabilities that evolve in time. You can ask, what is the chance of finding a particle here at this moment? But in Wheeler-DeWitt, there is no time. So, what do probabilities even mean? The universe's wave function assigns amplitudes to entire spatial geometries. But what does it mean to say that one geometry has a higher amplitude than another? Without time, there is no clear way to interpret probabilities dynamically. Some suggest that probability itself must be redefined in relational terms, but consensus is elusive. Experiment adds another layer of difficulty. Relativity and quantum mechanics both thrive because they make predictions we can test. Relativity predicts light, bending around stars, clocks slowing in gravity, waves rippling through space-time, all confirmed. Quantum mechanics predicts the spectrum of hydrogen, the tunneling of electrons, the interference of photons, all confirmed with uncanny accuracy. But Wheeler-DeWitt describes the entire universe. There is no laboratory outside the cosmos, no experimenter who can vary conditions and run trials. Testing it is almost impossible. Cosmology offers some hope. If Wheeler-DeWitt is correct, it may leave fingerprints in the structure of the early universe, in the cosmic microwave background, in the distribution of galaxies. Some cosmologists attempt to use simplified Wheeler-DeWitt models to calculate probabilities of inflation, or to predict how the universe's initial conditions might arise from the timeless wave function. But these efforts are tentative, and the data are not precise enough to give clear answers. The timelessness of the theory itself makes it difficult to connect predictions with observations. This leads some critics to argue that Wheeler-DeWitt is not a real physical theory, but a mathematical curiosity, a stop along the road rather than the destination. It may hint at something profound, but without a way to extract testable predictions, it cannot stand as a theory of nature. Others reply that it is still invaluable, for it forces us to confront the deepest puzzles: the absence of time, the role of causality, the meaning of quantum states for the universe as a whole. Even if it is incomplete, it illuminates the terrain of quantum gravity. There are also competing approaches. String theory, for instance, attempts to unify gravity and quantum mechanics, with extra dimensions and vibrating strings. Loop quantum gravity, Ravelli's field, tries to quantize spacetime itself into discrete loops. Both offer frameworks where Wheeler-DeWitt plays a role, but is not the whole story. In loop quantum gravity, the equation emerges naturally, but it is embedded in a larger picture where spacetime is granular and relational. In string theory, the timelessness of Wheeler-DeWitt intersects with the holographic principle, suggesting spacetime may emerge from deeper, timeless structures of information. Amid these debates, one thing is clear: Wheeler-DeWitt remains unsolved. Its timelessness is not a flaw, but a challenge, demanding new ways of thinking about physics. It forces us to confront the possibility that our most cherished intuition, that time flows, is not fundamental. The difficulty of the equation reflects not only mathematical complexity, but also the strangeness of a cosmos where the clock has no place. For those who work with it, the Wheeler-DeWitt equation is both frustrating and inspiring. It is a wall that resists progress, but also a window that opens onto new landscapes. Its very intractability hints that we may need new mathematics, new concepts, even new philosophy to grapple with the timeless universe. It sits at the boundary of our understanding, like a riddle whispered by the cosmos, daring us to listen. And so, the equation remains, scrawled across chalkboards, buried in dense papers, debated in conferences. It has not yet delivered a final theory, but it has shifted the question. The problem of quantum gravity is no longer only about merging equations. It is about reimagining reality. If Wheeler-DeWitt is correct, then time is not part of the foundation. Our task is to understand how time reemerges, how entropy, memory, and consciousness flow from stillness. That puzzle, unsolved and perhaps unsolvable in full, is the frontier of physics. As we move forward, we must consider not only the mathematical and experimental hurdles, but also the human ones. How do we live in a world where time is not real? How do we find meaning in a block where all is already written? That is the existential challenge of this timeless physics, and it is where science meets philosophy, where equations meet the soul. If the Wheeler-DeWitt equation whispers that the universe is timeless, and if the block universe tells us that all moments coexist, then we must confront one of the most intimate questions of existence. What becomes of freedom, of choice, of the sense that our lives are not pre-written but unfolding? It is one thing to accept that time may not be fundamental in physics. It is another to accept that your next decision, whether to lift a hand, whether to love, whether to forgive, might already be etched into the timeless structure of reality. To live as a human being is to feel that we are agents moving through time, shaping the future by our actions. We plan, we decide, we regret, we dream. We experience ourselves as causal beings who can change the course of events. Without that experience, life would feel empty, mechanical. Yet, in a universe where all moments already exist, freedom seems to vanish. The future is as fixed as the past. You do not create it, you merely discover it, as your consciousness slides through the block. Some respond to this with despair. If everything is written, then why strive? Why struggle? Why hope? If the ending is already there, what is the point of the story? But others find a subtler way to reconcile. They suggest that freedom is not about creating the future, but about being the kind of creature whose path includes deliberation and decision. You are not outside the block, altering it. You are part of the block, and the block includes you deliberating, doubting, and choosing. In that sense, free will is not an illusion, but a perspective. Your choices are real because they are the choices written into the pattern that is you. This perspective echoes compatibilism in philosophy, the idea that freedom and determinism are not enemies but partners. Even if the universe is fixed, freedom lies in acting according to your nature, your desires, your reasons. In the block universe, your decision to raise a hand is as real as the motion of the hand itself. Both are part of the structure. The fact that they coexist does not negate the choice. It defines it. Still, the tension is not fully resolved. For some, the thought that their entire life is laid out, every triumph, every mistake, every heartbreak, is unbearable. It robs the future of openness, replacing possibility with inevitability. Yet physics pushes us toward this view, not out of cruelty, but out of consistency. The equations do not permit a universal now that slices the real from the unreal. All slices are real. All moments are there. Consciousness complicates the picture further. The brain is a machine that anticipates. At every instant, it models possible futures, weighs them, and selects an action. This machinery depends on the illusion of openness. Without the sense that tomorrow is unwritten, we would not function. The very experience of freedom is an adaptive necessity, even if the block denies its ultimate truth. The illusion may not be fundamental, but it is essential. Dreams once again provide a clue. In dreams, we often feel free, making choices that steer the dream narrative. Yet upon waking, we recognize that the dream was pre-scripted by the brain's nightly patterns. The freedom we felt was real as experience, but not as creation. Perhaps waking life is similar. The freedom we feel is authentic to us, even if the cosmos already contains the outcomes. Our choices are not less meaningful because they are written. They are meaningful precisely because they are part of the eternal block. Some physicists and philosophers resist this determinism, pointing to quantum mechanics. Quantum events, after all, are probabilistic. The outcome of a radioactive decay cannot be predicted with certainty. Perhaps this randomness opens the door for genuine freedom, for futures that are not yet real. But even here, the Wheeler-DeWitt picture is merciless. If the universal wave function contains all possibilities, then all outcomes exist timelessly in superposition. The randomness is ours, not the cosmos's. To us, futures branch. To the block, they coexist. So, where does this leave us? Perhaps with a different conception of freedom altogether. Freedom is not about altering the future, but about inhabiting it fully. It is about owning the choices that are inscribed into the block, not because you could have done otherwise, but because those choices are you. To live freely is to align with the pattern of yourself, to embrace the story as it unfolds through your consciousness. This vision is humbling. It suggests that we are not sovereign authors, but characters in a cosmic book already written. Yet characters are not meaningless. Hamlet's decisions are not less real because Shakespeare wrote them. Frodo's burden is not less heavy because Tolkien scripted it. Within the story, choices matter deeply. They define character, they create meaning. We are the same, characters in a block universe, living choices that are both eternal and deeply ours. In this way, timeless physics does not erase meaning, but reframes it. It asks us to see freedom not as the power to escape the block, but as the power to live within it, to bring awareness and love to the choices that are eternally ours. If all moments coexist, then every kindness you show, every act of courage, Every word of forgiveness is preserved forever. They do not pass away. They are part of the structure. You cannot lose them. They cannot vanish. And perhaps that is enough. Freedom may not be the ability to create the unwritten future, but it is the ability to live fully in the eternal present that is written. The illusion of openness, the experience of deliberation, the sensation of causality. These are not errors to be corrected, but gifts to be cherished. They give life its texture, its urgency, its poignancy. Without them, the block would be cold stone. With them, it becomes story. As we near the end of this journey, the question turns not only to physics but to meaning. If time is not fundamental, if freedom is not creation but participation, then what is the value of life in a timeless cosmos? That is the question we carry into the final part of our exploration, where the stopped clock returns, and we reflect on what it means to live when the universe does not flow. Return for a moment to the room with the clock whose hands have frozen. It hangs silently on the wall, refusing to tick. At first, the stillness seems wrong, as though something essential has been lost. But if you sit quietly, you notice that the world continues. Sunlight drifts across the floor, shadows lengthen and fade, the air stirs with faint currents. The clock is stopped, yet life goes on. This image, simple and domestic, is the metaphor we have carried through our long journey. For what physics suggests at its deepest level is that the cosmic clock itself may also be stopped. Time, the most familiar rhythm of our existence, may not be fundamental at all. We began with Newton, who saw time as absolute, an eternal river flowing everywhere at the same rate. We passed to Einstein, who bent time into relativity, showing that clocks tick differently depending on speed and gravity. We descended into the quantum world, where particles shimmer with uncertainty, and saw the clash between relativity's curved space-time and quantum mechanics' probabilistic haze. Out of that clash, Wheeler and DeWitt dared to write the wave function of the universe itself, discovering that time vanishes from the equations. And so, we arrived at the haunting possibility that the cosmos is timeless, a frozen hole, a block in which all moments coexist. We have followed entropy's arrow, the rise of disorder that gives us the illusion of flow. We have traced the brain's weaving of memory and anticipation, creating the fabric of past, present, and future. We have listened to Carlo Rovelli's voice, telling us that time is not fundamental but relational, arising from correlations between subsystems. We have contemplated the block universe, where every event, birth, death, joy, sorrow, exists eternally, equally real, preserved in the structure. We have wrestled with the dissolution of causality, the erosion of free will, the unsettling possibility that choice itself is inscribed into the block, not created afresh. And yet, through all of this, a paradox has remained. Time may not exist at the foundation, but it exists for us. It may be an illusion, but it is an illusion so vivid, so necessary, so all-encompassing, that it defines what it means to be human. Without time, there is no memory, no growth, no love, no loss. Without time, there is no story. Even if the cosmos is timeless, the flow of time is the medium of our lives, and for us, it is real enough. Perhaps this is the lesson of timeless physics, that we must hold two truths together. On the one hand, the universe does not flow. It simply is, a frozen wave function, a block of being without becoming. On the other hand, our experience of flow is real, emergent from entropy, consciousness, and relation. It is not fundamental, but it is not false. It is a perspective, a lens, a way of inhabiting the stillness. The stopped clock becomes a symbol of this paradox. From one perspective, its hands are motionless, its mechanism inert. From another, the room around it is alive with change, and the absence of ticking is irrelevant. The cosmos may be the same. From the timeless perspective, all is still. From the human perspective, everything flows. Both views are true, though at different levels. Both must be held if we are to glimpse the whole. There is comfort here, too. In a timeless universe, nothing is ever truly lost. The moments we treasure, the laughter of childhood, the first kiss, the last farewell, do not vanish into the abyss of the past. They remain, etched into the structure of reality, as real as this very moment. To live is not to create fleeting sparks in the dark, but to be part of an eternal mosaic, each piece preserved forever. Death itself is less final in such a cosmos, for the moments of a life are not erased, they remain, eternal coordinates in the block. And there is humility. To accept a timeless cosmos is to recognize that our intuitions, so central to our daily lives, are not cosmic truths. The flow we feel is not written into the foundations, but painted by the mind onto the canvas of stillness. We are finite beings, bound to perspective, unable to see the whole. The universe is not a river carrying us along, but a sculpture we move through, mistaking our path for a current. In the end, perhaps the greatest gift of this vision is not certainty, but wonder. The Wheeler-DeWitt equation does not solve everything. It remains unsolved, ambiguous, controversial. But it opens our imagination to possibilities beyond intuition, reminding us that reality is stranger than we can easily grasp. To live in such a universe is to live with mystery, to accept that the deepest truths may be forever beyond us, and to find beauty in the not knowing. And so, the clock remains stopped, and yet the world continues. Time may not exist at the foundation, but it exists in the rhythms of our lives. The cosmos may be timeless, but we are temporal creatures, and our stories matter. The illusion of time is the most generous of illusions, for it gives us narrative, meaning, and love. Whether or not it is fundamental, it is the medium in which we live and breathe. Perhaps then, we need not fear the silence of the stopped clock. Perhaps we can learn to hear its stillness as a kind of music, subtle and eternal beneath the ticking of our days. The hands may never move, but within the timeless whole, every moment shines forever, and we, walking through them, give them names: yesterday, today, tomorrow. The journey ends here, but the story does not. It was never flowing toward an end. It was always present, always whole, waiting for us to arrive.